Then in the beginning of this year, I was for a few months in Vancouver, Canada, and there I gave a lecture on parallel systems, and I worked on FPGA virtualization. And FPGA virtualization can be a little bit compared to what you know from Java virtual machines. So that you have a universal description like bytecode, it's a different thing what we have here, but like a universal description, and that you can run this on multiple different FPGAs for different vendors, for example, and how to do such a thing. That's what I worked on. And something, this is a thing I started some time ago, and I will continue here. This is high-performance stream processing. So this is an example how you could consider to do database acceleration. So if you have, let's a query to a database where you say, where name, give me all records where name is John and age is larger than 42, then you have a string compare, you have an integer compare, maybe you want to sort the result. So each query represents basically a different data flow problem, and I want to compose this data flow dynamically by stitching predefined operator modules together. And I worked on something where I have a 300 megahertz data path running at 512 bits. This gives you 20 gigabytes per second. But you do all these comparisons in a pipeline processing thing. So if you consider the aggregated throughput you can achieve, it's not good for all queries. Yeah? So it's not like necessarily the thing of database you use for accelerating Facebook. You would do things differently there. But if you think of data warehouse applications where you have enormous data sets, that's the thing you want to do. Yeah, well, and since September, I'm a new lecturer here in the APT group, which you probably know, which is like Steve Weber. Okay, hardware projects. What I thought could be goals and what the content should be. First of all, it should be fun projects. Yeah, so it's not like you get a mark at the end of the day. It's not like I want to push pressure or anything on you. It's like jailing your creativity. If you have good ideas that might fit to the things I do, then I think it's a good thing to get together. And you should learn a little bit how to build hardware software systems, which is common for all embedded systems you have. It's not only your smartphone, it's your microwave, it's everything is a hardware software system, and these days an embedded system. And you could imagine to do many different things. And another important thing is with FPGAs in general, I will focus on this, as this is my research topic, and that's where I feel most comfortable in, is it's a way to do computing without processors. That's unusual for you folks. Yeah, when you say you solve an algorithm, this means type in C code, Java, whatever, and run it on a processor. And believe me, this is not the only solution, and most often it's not the best solution to take simply a processor to do things. The problem is many problems you have in our algorithms and systems you have to solve, you are power bound in these days. Doesn't matter if it's supercomputers, doesn't matter if it's an embedded mobile system, power consumption is the ultimate technology driver at the moment. So it's in these days it's not a problem to fit billions of transistors on a single chip. The question is how many of these transistors you can use for computation or to solve a problem. And that's the by far more essential problem. And there are things that can do low power processing better than ordinary processors. Okay, then within this project we will provide you access to hardware, which means physically boards, like such a toy. So this is a board, I have a few of those, not that many, but this is a little bit things you used already here, like it contains 2 ARM cores. You can run a full-blown Linux on it, but it contains also, around this ARM cores, reconfigurable fabric, an FPGA. And how this looks like, I will come later a little bit to this. Yeah, then, preferable, you have own ideas for project, that you say, oh, that's a problem I want to solve, that's a system I want to build. Now then come, drop me a mail, and we think to build a solution together. That's the thing, but if you say, oh, I just want to look into what is this, to get familiar with this, I will prepare a couple of projects that you can pick off and get, let's say, a guideline to do this. Yeah, so that's the overall big picture. And Robert was so kind and set up the website, and I will put in more and more information. I would also put these slides there. If you Google for this Ultimate Programming Workshop, there's also a link to this website. Yeah, so you don't have to write something. Okay, you already used FPGAs in your undergraduate courses. Yeah, but you used this as an ASIC replacement. You haven't really looked into what is an FPGA, what else can you do than simply, let's say, emulating a CPU. But you can do a little bit more. First of all, an FPGA is an abbreviation for field programmable gate array. Well, gate array you could imagine, yeah, it's an array of gates. Okay, what means field programmable? Field programmable means that you can define the functionality of this thing after production in field on the customer side. Yeah, it's not like Intel that produces an Atom processor and ships it to their customers, everything predefined. No, here you do this after production, to do the final customization. And it's useful for small volumes. Yeah, so if you cannot afford... Okay, how does it look inside? That's a screenshot from a tool, a design tool. Typically you don't see this. It is a little bit, if you want so, like if you do software programming, you don't go necessarily into the assembly code that's produced by the compiler. Very, very seldom you do this. And here it's a little bit the same. You don't look really from the stuff you program, you design how it really looks on the chip. But nevertheless, if you do so, it gives you like an impression how the whole thing works. So logic is implemented in lookup tables. That's on the next, or one of the next slides that explains this. Now that are basic cells just to implement any kind of logic, but they can only implement very little logic on gate level. AND gates, OR gates, counters, something like this. Okay. Then you have such things. This is called a switch matrix. Yeah. This is used to program interconnections. This gray stuff, this is wires. This highlighted wires are used wires at the moment, and you can basically program connections. This is nothing else as multiplexes you can program. Yeah, and you can draw basically a path across the chip to route certain nets. Okay. In addition, you have dedicated blocks like multipliers that are useful for arithmetic, but you also have blocks for memory, for example. Yeah, so typically a memory block in these days has something like 4 kilobytes of memory. You have 2 ports, you can read and write at the same time. Or if you have a processor, for example, you can read 2 operands, A and B, and you cannot write a result back, you need it. That's what you cannot do, but you can read, for example, 2 operands at the same time. Okay. So what is an FPGA? The technology, it's logic, arithmetic, and memory blocks, plus an interconnect network between that you can program. And this is the same picture, just zoomed out, okay? And the whole big block you see here is exactly the small square, and this blue box here would be the full FPGA. So in other words, you have thousands of these logic cells. And the area you see here is sufficient to host something like 2 32-bit processors, that you get an idea what you see here. So the FPGA that's shown here, and this is one I have in my office, this could host probably something like 50 times a 32-bit processor. But that's typically not the way how you use an FPGA. Yeah, it's the things can implement a processor, but you can implement algorithms much better than using a processor you load on them. I will come to a bit later. And this is how the chip looks like if you buy it. This is actually the chip is on the bottom, and this is the top metal layer. Yeah, and all these bumps here, they are later connection points to the outside world. Yeah, and if you put it on your PCB, it's actually flipped upside down on the board. This is done. And this is in the middle is the fabric, and here in the surroundings, this is all for I/Os. And you have a lot of fancy I/Os, like some of them can support several tens of gigabits data rate. This is quite a lot. Yeah, yeah, so you get hundreds of up to hundreds of gigabytes per second in and out, depending how you design your system. Okay, very shortly, I had this slide before in this ultimate programming, but how you, just to make it complete, how you implement logic. So the basic building block to implement logic is a lookup table. And the thing works very simple, like what you learned in the first semester, how an AND gate or an OR gate works. You simply look in the truth table to say if two inputs are, for example, for an AND gate are 1, then you say the output is 1, and in all other cases it's 0. Yeah, and you implement logic on the FPGA inside the logic cells exactly in the same using the same idea. Yeah, so and what you do is you have basically a multiplexer, or you can see this as a memory, and you address which table entry will be put to the output. Yeah, so you access basically a table entry which will be put to the output. And if you want to implement, let's say, an AND gate, well, that's if all inputs are 1, for example. Yeah, and if it's an OR gate, this means whenever you have a 1 at the input, you put a 1 at the output. Yeah, it's nothing else. And, well, you can implement any Boolean function unless it fits into these 4 inputs. And if the 4 inputs aren't sufficient, well, no problem. You can go to the next lookup table and build a bigger piece of logic. And you don't see these things. This is just like if you write code and it requires a certain amount of memory later. Here it is like how much logic you consume. And you just count how many lookup tables, for example, are used. Okay, that's the only thing, but it's not that you implement lookup tables directly. There are tools that do this, huh? So you can program later that you can do counting, comparisons, arithmetic, and so forth, but you don't necessarily program these ones. This is done by tools. It's just to see how an FPGA looks inside. The only thing, this is, let's say, these 3 bullets are the most important things you should take away from this one, even if you don't continue with FPGAs. But what the main difference is, an FPGA is rather slow, but it is brutal parallel. Typically you have thousands or a couple of thousand instructions running in parallel. Yeah, so that's the catch. You are, let's say, an order of magnitude slower with respect to clock speed, but you are several orders of magnitude faster. Typically, for most applications, you get a speed up in the range of 100 times, if the problem fits to an FPGA, not all fit. Yeah, the I/O throughput is not that high as compared to many other things, like a GPU has very much I/O bandwidth. You know how much a GPU has? It's some of the high-end GPUs have 200 gigabytes per second. This is a lot. This is really a lot. But this is also one of the reasons why these things burn that much power. Moving data around across the system simply takes power. Yeah, and this is, it's not a good idea, but GPUs have to do this because of their programming model, which is not necessarily the best for all problems. Yeah, but FPGAs have, depending on which one you choose, they have quite a little bit on-chip memory, like caches if you want so. But as I showed before, these caches or these memory blocks are available in small portions, and you can read and write from them in parallel. And this gives you an aggregated memory throughput in the range of terabytes per second. So you can say typically per megabyte you get 1 terabyte per second. Again, read and write at the same time. So on chip this is quite cool. It's a little bit difficult to program, and you use typically hardware description languages, but high-level programming languages like C++, Java, and so forth is coming up. They are very good for number crunching problems that are data flow oriented. They are not that good for control flow dominated stuff. Still, you can put a processor, for example, on them, and you could execute anything. But let's say if you have an operating system kernel where you have lots of if-then-else constructs, yeah, then this is something that fits better a CPU. But if it's something like dump number crunching, that's perfect for an FPGA. Okay. I had the slide before. So if you compute, if you write a normal program, yeah, and you translate it to want to run it on a normal CPU, like shown here, yeah, then actually Your compiler translates your code into machine code. I wrote assembly here, yeah, but each line actually represents an instruction that is decoded by the processor and then executed. Okay, this works fine, but if you go for an FPGA, you typically would do it in a different way. Yeah, what you do is you start to do something like a pipeline processing. So for example, here is a Boolean function where you just want to take the least significant bits. So from a vector, you just pick the least significant bits. Yeah, and this is not necessarily a function. Yes, or why? Well, this is just wiring. Some things you just do in the packet. Data movement is not a move instruction. It is just a link or some wires you route between different functional blocks. Yeah, and then you can put your adder, your multiplier, and so forth. Yeah, your adder and your multiplier, and you can build a pipeline in that direction. But that's one thing. You could also exploit parallelism by instantiating it multiple times. So in principle, you could run the whole loop body basically in parallel and unroll it. Yeah. If you want, you can also build dedicated instructions. Nobody tells you that an instruction necessarily is only addition or multiplication. You can have a multiply add. You can do this. It's not necessarily good. It's a trade-off. Because as more work you do, as slower this block might become. Yeah, so in other words, programming from FPGA is more a little bit engineering than classical programming. Have skin color or not. Skin color has a quite significant pattern, and this can be recognized with this algorithm. And if you do this in software, it's depending on how you implement this, it's about 20 instructions per pixel. Yeah. Well, it is data dependent. So if you would implement this algorithm here, then you say, if this condition is true and this condition is true and this and so forth, then you say it's skin color. So in principle, if this condition already fails, you don't have to process the rest. Yeah, you would jump out. But if it will be skin color, you have to go through the whole thing. Yeah, so it's a little bit like if you want to say something like average, worst case, or whatever. So that's not a constant thing. Yeah, but let's say it's 20 instructions per pixel. So if we consider a pixel clock of 50 megahertz, this gives you 1 giga operations per second. Or if you have a 100 megahertz pixel clock, this is still a little bit less than HD resolution. HD resolution is 140 megahertz. Yeah? So we talked about in the range of 2-3 giga operations per second what you need for an HD video stream. There's one cool thing here. If you consider you have this task here with an accumulator, this is something like a global state in the sense that it picks data from all iterations you have. So if you do such a thing, yeah, with SIMD instructions, you still have to think about how you get the zoom within each SIMD stage. And then, if you do multi-threading, you have to produce the zoom over all of this task. So you need an add-reduced tree or an add-reduced tree or whatever. But it gets a little bit difficult to do this. And here, if you do it in this pipeline processing, even if it's a global state, it's kept locally because everything passes by anyway sooner or later. Yeah. So quite often you have problems, and many real-world problems, optimization problems, are like this. For example, that you have an error, and the error you compute goes into the next iteration or something. And this is where FPGAs are very good for. That's their programming model. And big differences. An ALU is controlled by a program counter. Yeah, you program counter that points to the instruction and basically do single cycle operation, and you see that the programming isn't at the first place not necessarily too much different what you know from ordinary languages. Of course, the syntax changes, and a couple of times you have to think about that you have actually logic, but you can use symbolic variables and all these things. Okay, so I told you that FPGAs are a wonderful thing. Why is not everybody using them? Yeah, which could be your question. Well, first of all, this stuff has a massive overhead. Whenever you do something programmable, it has a significant overhead. It doesn't matter if it's an FPGA, a GPU, or any processor. Programmability always comes with an overhead. Yeah? In terms of an FPGA as compared to an ASIC, where ASIC would be that you just have one specific, or a chip that's done for one specific task. Here you have something that is reprogrammable for many different things. Yeah, and this reprogrammable stuff, for example, all this wired interconnects I showed you, this draws a lot of, produces a lot of overhead. And this is really significant. And a few years ago, people explored this. They took a couple of standard circuits and they optimized this for FPGAs and for ASICs. And the chip area was something like 20 times. The thing brought 10 times more power, and it was even much slower. Yeah, so it looks terrible. But if you would go for a processor, it's even worse. Yeah, so for example, if you consider a processor, it has, let's say, 100 different instructions, but each clock or operational cycle, you use just one of the instructions. So all the rest is pure overhead. Yeah, so if you only use load and store, if you want to do, let's say, memory movements or so with your processor, yeah, you use only very little of the whole functionality. So you won't use the floating point unit. This would be pure overhead. So in other words, having things programmable always comes with an overhead. But this doesn't mean that reprogrammability is a bad idea. It depends how you use the whole thing. So if you have, for example, a big complex system, let's say your office application, yeah, you use so many different software libraries only for a very short time. Yeah, so what you do is by reprogrammability, you do time sharing of the resources. And this makes it better again. So if you would consider you have lots of complex functions that you need only very seldom, and you would put this into a chip, then the chip would be infinite in size or really huge. Yeah? So reprogrammability would be an answer to this one. Yeah, so, but it's important that you try to get a feeling when things should be programmable and when maybe an ASIC is the best, and you have a huge design space there. Okay, and that's what I mentioned, that FPGAs allow you to actually have reprogrammability of the hardware at runtime. And that's often called partial runtime reconfiguration. That's the stuff I work on. I don't want to go too much into detail, but the way how it works is you implement your system and you leave resources unused, and into this area or resources you can place your modules later as they are needed at runtime. Okay. I have one nice example. That's work I did on my own for research, and this is large problem sorting using FPGAs. So this is large problems. We talk about sorting problems in the size of gigabytes, maybe terabytes. Yeah? If you consider we have a huge database. Yeah? And if you work with databases, if you use joins, for example, you have to sort. You might have to sort, or the result is always sorted by certain means. Yeah? And you all learned the best sorting algorithms are, like quicksort, is time complexity n log n. And you always accepted this. Yeah. Well, you can even sort in constant time. You can everything sort in a single clock cycle, in principle. It's a question how long the clock cycle is. Yeah, but you could do all the, like bubble sort needs n square comparisons. Yeah, you could do all the n square comparisons in parallel. You can have n square compare cells. And then you simply look up, with respect to the output flags, what value you have to pick out. Yeah, so you could do this, but it's not necessarily a smart idea. Okay, so the trick would be, what about taking log n sorter cells to get linear time complexity? In most cases, I don't need to go faster than linear. Why? Well, the data has to come in over an interface. That's you read from this, from a network device. Yeah, so data comes in sequentially. This is linear time complexity. So I don't have to go faster than this one. Yeah, and the sorter I built is very simple. It's a 5-row based merge sorter. Takes the input, sorted input sequences, produces an output sequence of double the length. And to be honest, that's not rocket science. This is how people sorted in previous times using magnetic tapes. Yeah, so you can consider this as a magnetic tape with tokens, yeah, and you take two magnetic tapes, sort this together and write on a result tape. And if you are done, you put this into a long chain, and so you repeat this, produce another sorted sequence, and then produce 4 times longer sequence, and so forth. And the tricky part, what I did, is to make this sorted cells very fast. So this whole thing works with 2 gigabytes per second. And there are some tricks how you use this memory, how you build this memory structure, do the data movement. I don't want to go into detail because you would get it not in your brain. Yeah, but that's how you can implement a sorter in a pipeline fashion. And this fits very well to an FPGA. Point 1. Point 2 is, one thing you see here is that I need different amounts of memory. And that's a nice thing with this reconfigurable stuff. I can allocate memory to processing elements as I need. It's not that I have a GPU or multi-core cache architecture to follow. Yeah, so Intel defines for you where you should take the memory. And if your problem fits to this, wonderful. If it doesn't, you have a problem. Yeah, but here you can assign the memory that's available on the chip as you need it for your application. And if a later stage needs more memory, well, you simply allocate more memory to it. And that's a really powerful thing. Another thing is also you can implement any arbitrary data dependency on an FPGA. While if you use a GPU, for example, everything is done via shared memory. This is good for some things, but not for everything. Okay, so I don't want to go too much into detail, but if you have the sorting thing, what this first thing produces is fully sorted sequences, and if the problem is too big, then it fits then what can be held inside the chip. You have to write this to external memory. Okay, and that's what you do in one step. And if you have produced all your fully sorted sequences, you can merge them together, sort them together in one final step, or multiple ones depending on how big the problem is. Okay, and this is an interesting thing where you can use partial reconfiguration, because this step runs after this one has completed. So I can use the whole FPGA to solve this problem, write into memory, reconfigure the thing towards this one, this sorted tree, and why does this help? Well, I can spend more resources in each step, so I can solve a bigger problem, or I can solve the same problem using a smaller chip. Yeah. And that is where it helps. And I don't have put results here, but my one was faster than any GPU implementation or self-processing implementation. And I thought at 2 gigabytes per second, and we want to scale it up for a single node to something like 8, maybe 10 gigabytes per second. And if you would then put together a dozen FPGA boards, if you can get a disk array connected that provides you the speed, you can build the fastest sorter, and this would achieve the throughput. What you can, the fastest sorter that's out at the moment is at Yahoo, and that's a machine with 2,200 Xenon processors, a very big machine. And just taking a dozen FPGA boards with a lot of SATA disks, solid-state disks, would achieve the same performance, to give you an idea of what you can get. Okay, this was just an appetizer for FPGA technology in general. We are here a little bit to talk about also the hardcore projects. And so the overall idea is, I encourage you to come up with own ideas. Don't have to be right away, but it's like, say, an offer from our side. And if you have an idea, you can come to me, drop me a mail, and you should do your own things. But if you think, okay, maybe it's interesting, but I have not a project right away, or you have to do this as well. But that's not everything you can do. If you say that's your ALU that gets the 2 operands A and B, what you could do is, well, you simply add a multiplexer, and you can add your own instructions. Yeah, you can have customized instructions. Yeah, for example, if you do crypto algorithms, you have a lot of bit shuffling algorithms, yeah, or the S-box lookup, for example. Yeah, you could have a dedicated instruction for this. And this gives you quite some speed up. Yeah, and to use this is relatively easy. Yeah? You simply access the two operands, put this to your own hardware module, and depending on the instruction, you use simply a multiplexer to select your own instruction. It's that easy. And that's not the only thing you can do. You can imagine, and that's what I did, is that you create kind of a, yeah, this, well, I don't go into this one, but that you can consider that you exchange these blocks. So depending on which program you currently execute, you can even execute or start different customized instructions. Yeah, and I have a few examples where I did this. So for example, consider you want to do a 30 or 64-bit XOR gate. Yeah, so basically it's the parity. You want to count over a 64 input vector. This is this vector plus this one. You want to know if the number of bits is equal, odd or even. Yeah. Well, if you do it in software, it's quite a lot of instructions, and the idea is just adding a tiny little bit, a dedicated instruction might help you. And if you want, so this customized instruction is the best of the RISC world and the CISC world. Yeah, so the nice thing with the RISC is it's small, lightweight, but fast. Yeah, and CISC allows you to do a few more complex things. And here the idea is, okay, you keep it as lightweight as possible, and only the things where you know I need, then you put in. Yeah, so if you have a CISC processor like your x86 machine, it has so many instructions that if you would disassemble your program, you rarely use, or a lot of these instructions are never ever used. And here you can just put in what you really need. Okay, so that would be processor design. Another thing at this point, you square from the last iteration, add the original point, and you do this as long as your radius or the vector length exceeds 2, or you have an upper bound. That's really the whole algorithm. And if you do this, it looks this fancy. Well, this is not a fancy one if you go, but if you know Mandelbrot, you know that you can zoom in into each depth level, and if you want to have it looking a little bit more fancy, then the number of iterations you use here is actually equivalent to a colorway imputation. Yeah, that's everything you want to do. So it looks very easy at the first. Okay. Another thing is, typically a lot of students are interested in robotics. That's what I experienced in Norway. And one thing where FPGAs can help a lot is machine vision, or you could say give your robots eyes. Yeah, and they are good for something like noise reduction or anything that has to be done to pre-process before you start with your actual algorithms. You can use this for segmentation or any feature extraction. You can consider to do even stereo vision, or you can even consider if you have a moving environment that you do use things like motion estimation to figure out your own speed. Yeah, so for example, all these Mars rovers that you send to space, they cannot rely on GPS. That's not available on Mars. Or GPS is only working or isn't working in buildings. So you must have other ways to navigate. Yeah? If you want to measure speed, you can of course say, I count how often my wheels are rotating. Yeah, but if you have a slippery ground or if you drive some curves, that's not going to work very nicely. So typically optical